Dear students, today we will discuss about Compton effect. The Compton effect is the conformation of photon models. In our previous some videos we discussed about the pair production and about photoelectric effect, in which we discussed the photon as a particle. Now here the Compton effect is further its conformation. We said that the Compton effect is the conformation of photon model. Conformation of photon model. So when we says that the photon is a particles, then we must think about its two properties. That is, it must have energy and it have momentum. So both these are the properties of particles. Okay, so we know that there are some equations, and like E square is minus P square C square is equals to M square C square. You are familiar with this type of equations. And then energy, you can say that this is also very familiar equation, mc square over 1 minus v square over c square. And then in the same way, p momentum is equals to mv divided by 1 minus v square over c square. So these are the relativistic relation of momentum and energy. If you didn't know much about the relativity, then you know about the non-relativistic equation. E is equals to 1 by 2 mv square and p is equals to mv square, and then we can say that E is equals to p square by 2m. So these are the non-relativistic version of these relativistic equation. If you could somehow solve these equations, then you will come to this relation, which is the relativistic relation of momentum and energy. So the particle, you know that when we consider the photon as a particle, then we consider, if when photon is a particle, then it has zero rest mass. Then is energy, that is C gamma, that is the energy of photon, then it must be equals to P gamma C when mass of photon is equals to 0. And then what about the momentum of the photon? P gamma will be equals to E gamma over C, and you can write this relation further. You can modify this relation and you can write it like P gamma will be equals to H mu by C, and then further you can simplify it and you can write it like it will be equals to P is equals to H divided by lambda, wavelength of gamma. So this is the most important relation between the momentum and the wavelength of the photon, in which we are interested. That is, in Compton effect, we will discuss about the shift in the wavelength. That is how wavelength shift when we will discuss about the Compton effect. So now we come to the our basic problem, that is the Compton effect, that what is the Compton scattering. Now we will discuss what is the Compton scattering. Okay, the Compton scattering, we can say that when X-rays photon of highly energetic radiation, which are highly energetic. Okay, when these photon falls on atom or shine the atom, and then it gives this energy, it has too much energy, and when it gives the energy to the electron, because these are highly energetic radiation, then electron can easily escape away from the atoms. So it can easily knock out the electron from the atom. So as you know that the S-ray photon, which are highly energetic, and these have the very uh, large amount of the energy, while the binding energy of electron is about 10 to 13 in electron volt range. So these highly energetic S-ray photon can easily knock out the electron from the atom. So here the few things happens when the S-ray photon knock out the electron from atom. The first thing which happen is the violation of classical classical Thomson scattering. Classical Thomson scattering. So when Compton effect occurs, then it violates the classical Thomson scattering. Now I will tell you that which is the Thomson scattering and how it get violated by the Compton scattering. So here we consider the electromagnetic radiations. Electromagnetic radiations, you know that it has the electric and magnetic field components, and here we consider, in the case of Thomson scattering, we consider that these are low energy radiations. These has very little amount of energy. When these are of the low energy radiations, then we can say that magnetic component is very little, or it's very small, its impact is very small. So when the magnetic field is very weak, when magnetic component is very small, then we can say that Lorentz force which is the combination of electric plus magnetic field component, becomes very weak, become very small. So these are low energy radiation when falls on an electron. Here we consider the electron as almost free electron, and we consider the electron at rest. So these electromagnetic radiations falls on the electron. Then, as these are the low energy radiations, so the magnetic field is very small. It's so here the dominant field vector is the electromagnetic field vector. So the electric field, this electrostatic field, shakens the electron field of the light. So electron get radiate. So it's when it shakens the electrons start to and fourth movement or motion about its mean position. So the pattern of this motion is such that it start to radiate the radiations. As you know that the moving charge particles emit the electromagnetic radiation. So when these incoming electromagnetic radiation, which are the weak electromagnetic radiation, it shakens the electron, and electron start its to and fro motion, and motion of pattern of this motion is such that it due to this motion it emits the electromagnetic radiation. So it will emit the electromagnetic radiation in all directions. Okay, so it will emit the electromagnetic radiations in all direction. So the formula for the scattering Thomson scattering cross section can be written as a function of angle theta, which is the angle theta is the angle between the incident photon directions and the photon that emerges in different directions. So this is the angle theta. Angle theta is this one is the original direction, and these are the photon which emerges in other direction, which emerge in other than the incident direction of the photon. So the scattering Thomson scattering cross section can be written as d sigma over d omega. It will be equals to E over mc square into whole square into 1 by 2 1 plus cos square theta cos square theta. So this is the angle theta is the angle between the incident direction of the photon and the photon that emerges. So this scattering cross section has the unit of area, that is per solid angle. So the here we can think of the area. You can the area should be thought of as area that captures from the incoming beam. That is, this is the incoming beam of the radiation. So we says that this is the incoming beam of the radiation, and this one is the area. So this area captures this incoming beam of radiations. So it emerge. So this incoming beam of this is the incoming beam of energy. As you know that these radiations have the energy, so we can say that this area is correspondingly emit the energy into this solid angle. Okay, this is the area which captures these incoming radiations into this small area, into this small solid angles. So this area correspondingly represents the energy. So radiation represents an area and area represents an energy, because you have the beam coming in the form of electromagnetic waves and through a little area, through this one area. So some energies goes into this area. So some energies goes into this area and you get it this energy. But here the most important thing about this classical Thomson scattering is that it is not quite accurate. So what is the wrong what is wrong about this classical Thomson scattering? When when we go to the highly energetic electromagnetic radiations, when we go to the high energy high energy radiations, then there is the violation of classical Thomson scattering. So now I will tell you that how highly energetic, how when we go at higher energy electromagnetic radiation, how these highly energetic electromagnetic radiation violate the classical Thomson scattering, uh, and instead of classical Thomson scattering, we observe the Compton scattering. So the thing which is pretty wrong about the Thomson scattering, Thomson classical scattering, at which is due to the low energy electromagnetic radiations. So as you know that these electromagnetic radiations when checkens the electron, and as a result the electron emit the electromagnetic radiations. So the energy of these electromagnetic radiation which emerges from the electron when the low energy electromagnetic radiations strike this electron, or so these electromagnetic radiations and the incident beam of electromagnetic radiation have the same frequency or have the same energy. So energy of incident beam is the same, equals to the beam that emerges. Okay, both have the same frequency or same energies at when we use the low energy electromagnetic radiation. So this is the property of this scattering. This is the property of Thomson scattering. So but this properties goes wrong when we use the high energy radiation. High energy electromagnetic radiations. When high energy electromagnetic radiations strikes the electron, then we get the frequency of incident photon beam or incident beam is different from the scattered beam of photon. So here the frequency is the different, wavelength is the different. So as a result, we get the shift in wavelength. So this fact was first observed by the Compton and that's why it is called as Compton effect. Now we will discuss the Compton scattering. So here we will discuss about Compton scattering. So in the case of Compton scattering, when the beam of highly energetic electromagnetic radiations, that is incident photon, which are highly energetic X-ray photon, which strike the electron. This is the electron at rest, and when these radiations strike the electron, then this is the original direction of radiation, then these incident photon get scattered in different direction and electron will get scattered in the different direction. So this is the scattered photon. This one is the scattered photon and this one is the scattered electron, and this one is the original direction of incident photon. Direction of incident photon. So as here you have seen that the incident photon and scattered photon, here we actually consider the two different photon. The incident photon has the momentum h mu and divided by c, and it has the energy E is equals to h mu. And while the electron which is at rest, its initial momentum is equals to 0, and rest mass energy, you know that it's equals to m naught c square. So the scattered photon has energy E is equals to h mu prime, and its photon momentum of this scattered photon will be equals to, can be represented by h mu prime divided by c. And electron has energy m naught square c4 plus p square c square under root, and it's now it has some momentum. So here the incident photon, which is highly energetic photon, gives its amount of energy to the electron which is at rest. So as a result, this electron will scattered by gaining an amount of energy from incident photon will scatter in the different direction, and photon will get scattered in different direction. So the scattered photon has different energy than the incident photon, and as a result it has different momentum than the momentum of incident photon. So momentum, here we can say that again we can make a diagram like this one. So for incident photon, this is the triangle for the incident photon, and this one is the for electron. So the photon make an angle phi with the incident direction of the photon, while the electron make an angle theta with the original direction of photon. So here the phi, so we can say that it will be equals to h mu prime by c sine of phi, and this one will be h mu prime by c cos of phi, and theta, this is the angle theta, and you can say that this is the electron has the momentum p, so this will be the p sine theta, and this one will be equals to the p cos of theta. So as the momentum, we can see that the energy loss in the energy of the photon, energy which is the loss by the photon, loss in the energy of photon, which will be equals to the gain in energy by electron. So it will be equals to h mu minus h mu prime will be equals to kinetic energy of electron. So in the same way we can say that there is the equation, momentum will be equals to E by C, which will be equals to h mu by C. So this one is the momentum of photon. Now this was the law of conservation of energy, law of conservation of energy. According to the law of conservation of energy, energy which is lost by the photon, incident photon, is equals to the energy gained by the electron, which is equals to h mu minus h mu prime, it will be equals to kinetic energy. So this is the law of conservation of energy, and momentum is of the photon is E by C, which can be written as h mu by C. Now we go to the conservation of momentum. So now when we go to the conservation of momentum of photon, and so we know that when we consider the momentum, unlike energy, it is the vector quantity. So it is the vector quantity, and so here we must need to incorporate the direction as well. So here we will consider, along with the magnitude of the momentum, we will also consider the direction of momentum is also very important. So in the in the figure, in the last slide, we have already incorporated the direction of the momentum as well. Whenever there are the two bodies or more than two bodies are involved in the collision, then we must consider the direction of the momentum, and so along with the magnitude, the momentum should also be conserved in direction. Conserved in direction. So there should be the two or three more than two mutually perpendicular direction. So in the last figure I already told you that this one is the so if this is the original direction of the photon, then this is the um, moment angle phi, it makes an angle phi, and electron momentum makes an angle theta. So this is the angle theta, so it has the momentum p, so this one is the p sine theta and this line is the p cos theta, and for photon it is equals to h mu prime by c cos of phi, and this one is the h mu prime by c, and this line is will be equals to, and this line will be equals to the h mu prime by p sine of phi. So here the direction we choose here are that of the, this one is the original direction of the photon and perpendicular direction and the horizontal direction. So the momentum must be conserved in the horizontal and in the perpendicular direction. So here we consider that if initial momentum of the photon, which is equals to h mu by c, so the scattered photon momentum is, that is scattered photon momentum is equals to h mu prime by c, and initial electron momentum is equals to 0 as electron was at rest, while the final or scattered electron momentum is equals to p. Now we go to the law of conservation of momentum. So here first we consider the conservation of momentum in horizontal direction. So in the horizontal direction, as you know that you can see from the figure, is equals to h mu by c plus horizontal momentum of the electron is equals to 0, while of scattered photon momentum is h mu prime by c cos of phi plus scattered electron momentum in the horizontal direction is p cos of theta. So this is our equation number 1. So this is the initial photon momentum, this is one is the initial electron momentum, and this one is the scattered photon momentum, and this one is the scattered electron momentum in the horizontal direction. Now we go to the perpendicular direction, conservation of momentum in the perpendicular direction. So in the perpendicular direction we can say that it will be like this one. In the perpendicular direction, initial momentum, conservation of momentum is the initial momentum in perpendicular direction should be equals to the final or scattered momentum in the perpendicular direction of both electron and photon. So in the perpendicular direction, the initial momentum of electron and photon both is equals to 0, while the final of photon will be equals to h mu prime by c sine of phi minus p sine of theta. So this one is our equation number 2. as you know already know about the angle phi and theta. Angle phi is the angle between the final direction of the photon and its the initial direction of the photon, and theta is the angle between the final direction of electron or scattered electron direction and initial photon moment, photon direction. Now we will solve the equation 1 and 2 simultaneously. So by solving equation 1 and equation 2. So by solving these two equations, you will get P cos of theta is equals to h mu minus h mu prime cos of phi. Okay, P, and secondly equation PC sine of theta is equals to h mu prime sine of phi. So this is our equation number 3. So in equation 1 and 2 we just multiply the whole equation 1 and 2 by C, and by rearranging the equation we get the PC cos of theta is equals to h mu minus h mu prime cos of phi, and from equation 2 by multiplying this by C the whole equation we get PC sine of theta is equals to h mu prime sine of phi. So now in the next step what we will do, we will square both equation, squaring both equation, these two equation, both equation, and you can say that equation A and this one is the equation B in equation 3, A B of 3, and when we square both and then adding them, after squaring we will add them and adding them. Now what we will get, now here we will do a little bit mathematic, and so first we square these equations. So by squaring equation A you will get p square c square into cos square theta. This will be equals to h mu minus h mu prime cos of phi whole square, and so this should be equals to p square c square cos square theta is equals to h mu square minus it should be equals to the plus h mu prime square cos square theta minus 2h mu into h mu prime cos of phi. So here we say that on this here we have done that a minus b whole square is equals to, we open this formula and we get h mu square plus h mu prime square cos square theta is equals to minus 2 h mu into h mu prime cos of phi. So as it is equals to a square plus b square minus 2ab, while when we square the equation b we get p square c square sine square theta, it is equals to h mu prime square sine square phi. So we consider both these two equations as our equation number 4. Now we will add these two equations of equation number 4. So when you add the two equation in equation 4, both equation, two equation of equation number 4, what you will get, we will get like this one, p square c square. From the left hand side equation, we will take the p square c square as a common factor, and then you have sine square theta plus cos square theta, and this will be equals to h mu square plus h mu prime square and sine square phi plus h mu prime square cos square phi minus 2 h mu into h mu prime cos of phi. So by the rearranging, you get cos square phi plus sine square phi, it will be equals to 1, and you get p square c square is equals to h mu square plus h mu square as a common factor. Then you will have within the bracket sine square phi plus cos square phi minus 2 h mu into h mu prime cos of phi, and then you will get p square c square is equals to h mu square plus h mu prime square, as this one will be equals to 1 minus 2 h mu into h mu prime cos of phi. So this will be your equation number 5. So now we have the two expression for energy. We have two different expression for energy. And these two expression for energy is, first one is E is equals to kinetic energy or plus m naught c square, and second one is the E, E will be equals to m naught square c4 plus p square c square. And you are familiar with both of these relation from the from theory of relativity, and now we will equate both these equations. So by equating, as both are the equation of energy, so by equating both these equation, so both are equation of energy, we can equate them. So when we equate them, what we will get, we not only equate them, we will also square them. We will equate them and square them. So what we will get, so by equating and squaring both equations of energy, so what you will get, you will get the expression when you equate them and square them, kinetic energy plus m naught c square whole square is equals to m naught square c4 plus p square c square. So when we open the square of this equation, we will get kinetic energy square plus m naught square c4 plus 2 into kinetic energy plus into m naught c square is equals to m naught square c4 plus p square c square. As you know that we open it by the formula a plus b square is equals to a square plus b square plus 2 ab. We used this one to open the square of kinetic energy plus m naught c square whole square. So from this equation you can see that we can cancel out the quantity of this one, as these are on the both side of equation. So our remaining equation of energy will be equals to kinetic energy square plus 2 into kinetic energy into m naught c square is equals to p square c square. So further we can make some addition into this equation, and as you know that the kinetic energy is equal to h mu minus h mu prime. So we can make this addition of kinetic energy into this equation. So by making this addition you will get p square c square is equals to h mu minus h mu prime square plus 2 into, in the place of kinetic energy we will write h mu minus h mu prime into m naught c square. So this is our equation number 6. So we can further solve this equation. So now we can equate the other two equations, and these two equations are, we can equate the equation 5 and equation 6, because both gives the value of p square c square, both are equals to the p square c square. So we can equate the equation 5 and equation 6. So by equating these equations we get h mu square plus h mu prime square minus 2 into h mu prime into cos of phi will be equals to h mu minus h mu prime square plus 2 m naught c square into h mu minus h mu prime. So here again we can simplify these equations. So first we need to write like it, this one, h mu square plus h mu prime square minus 2 h mu into h mu prime cos of phi. So we need to solve this one. So when we solve it, h mu square plus h mu prime square minus 2 h mu into h mu prime plus 2 m naught c square into h mu minus h mu prime. Okay, now we can cancel out some quantities because that quantities are on both sides of equation, and these are h mu square into h mu square, h mu prime square and h mu prime square. So remaining quantities we have minus 2 h mu into h mu prime into cos of phi will be equals to minus 2 h mu into h mu prime plus 2 m naught c square into h mu minus h mu prime. So again we can cancel out the 2 because the 2 is along with the whole equation. So our remaining quantity we can further simplify it, and it will be equals to, we can further write it like this one, h mu into h mu prime, and you can write it into 1 minus cos of phi. So by joining this one and this one, you will get the h mu prime into h mu prime into 1 minus cos of phi, and will be equals to m naught c square into h mu minus h mu prime. So our equation will be like this one. So we can say that this is our equation number 7. So now we can further simplify over this equation, and how we can simplify over this equation. We can simplify by multiplying equation 7. We can multiply it by h square c square in order to write in term of lambda. In order to write it in term of lambda. Why we want to write it in term of lambda? We want to write it in term of lambda because we need to find the shift in wavelength instead of frequency. So we need to write it in term of lambda or in term of wavelength. So we are going to multiplying the whole equation, dividing whole equation, sorry, not multiplying, but by instead of multiplying, by dividing whole equation by the quantity h square c square. So by dividing equation 7 by h square c square, to write it in term of lambda, we will get m naught c square into h mu minus h mu prime is equals to h mu prime into h mu into 1 minus cos of phi. So when we divide it by h square c square divided by h square c square, so divided by h square c square, so we can write it like m naught c uh, dot c. Instead of c square, we can write it c into c divided by h into h, and here the c square is again c dot c, and here we can take the h as a common and mu minus mu prime. So here you will get h square as a common and mu minus mu into mu prime into 1 minus cos of phi divided by h square c square. So here it will be cancelled out. Again here you can see that we can cancel it by this one and this one by this one. So your remaining equation will be like this one, m naught c divided by h, and this one c will get into this equation mu by c minus mu prime by c. So it will be equals to, again, and this c square we can write it mu by c into mu prime by c into 1 minus cos of phi. And you know that mu by c is equals to 1 over lambda, and mu prime by c, so it correspondingly it will be equals to 1 over lambda prime. So making these substitution into above equation, we will get we can further simplify it, and it will be equals to, so making the substitution, we will get, it will be equals to m naught c divided by h into 1 over lambda minus 1 over lambda prime, and it will be equals to 1 minus cos of phi over lambda into lambda prime. So when we further simplify it, we will get we can write it like lambda prime minus lambda, it will be equals to h over m naught c into 1 minus cos of phi. As when we solved 1 over lambda minus 1 over lambda prime, we get lambda into lambda prime, so lambda prime minus lambda. So when we write it like this one, so by further simplifying, we get, it is here, this one is the h. So when we put these values, we get this one equations. So this equation, which is our equation number 8, so this is our main equation, and this equation is called as Compton effect. So this equation is called as Compton effect. So this equation was derived by the Arthur H. Compton in the early 1920s, and so he derived this equation in early 1920s, and the phenomena he described, which was the first, he was the first to observe this Compton effect. He used the highly energetic beam of the radiation to scatter the X-ray photon by an incident by the target electron, and so this effect was called as the Compton effect, and so it was the further confirmation of the photon model. And this Compton effect tells us about the shift in wavelength of incident photon and the scattered photon. So this was the violation of the classical theory, in which the wavelength and the frequency of incident and the scattered photon remains the same, but when we use a high energy photon, here is the shift in wavelength. So the scattered photon is have the different momentum and energy and wavelength as compared to the incident photon. So we can write this quantity as like the lambda prime minus lambda is equals to lambda c into 1 minus cos of phi. So this one is called as the Compton shift in wavelength. This is the Compton wavelength. So the Compton wavelength gets scattered, uh, shift by this factor, which is called as the lambda c. So lambda c, Compton wavelength, is equals to h over m naught c. So the Compton wavelength of, this is the Compton wavelength of the scattered photon. So this was all about the Compton effect, which was observed by the Arthur Compton in 1920s, when he used the highly energetic X-ray photon to knock out the electron from an atom. So he observed the shift in wavelength. So this was all about the Compton effect. Thanks for watching. For more videos, please subscribe our channel.